I'm going to look at the one proof I didn't do in class for one of my classes. Page 311, number 9. I'm going to show that a matrix and its transpose, so that's two separate matrices, have the same eigenvalues. So there's a little bit of background that you would have to do in order to do the problem. One thing is you look back in the book and find the section on transposes. And in this section, there's on page 50, there's a list of some attributes that transpose has. This is one of them, and we'll be using it, but I put it up there. But this is the kind of research that you need to do before you do a proof. Go find out all the information you can about transposes. Then you have to say, well, what does it mean to find the eigenvalues of a matrix A? And what does it mean to find the eigenvalues for A transpose? Ultimately, we want them to be the same, but you can ask the separate question, what does it mean to get them? So this is what it would be. If I want the eigenvalues of A, I solve this. If I want the eigenvalues of A transpose, I solve this. So the only difference is that one has an A and one has an A transpose. So this question here, show that A and A transpose have the same eigenvalues, can be reduced to the question, or the thing you need to show is show that the determinant of A minus lambda I equals the determinant of A transpose minus lambda I. If those two things are equal, then I'm done. Okay, so let's get going. This fact that I'm going to use here, determinant of A equals determinant of A transpose. So why is that true? Well, here's A. It's a bunch of rows. And when I create the transpose from A, I basically just take the rows and I turn them and they become columns. So the reason why the determinant doesn't change is when I go to compute the determinant of A, I can do my cofactor expansion along this row. And when I go to do my determinant of A transpose, I'm going to do my cofactor expansion along this column. And you can see how they're exactly the same. The stuff up here is going to be exactly the same as this stuff, and also the cofactors will be the same as well. So this is a nice fact for us. This will be a nice fact for us. Okay, let's get started. So what I want to do is I'm going to write proof. That indicates the start of my proof. I'm going to start with this symbolism, and I'm going to logically deduce that it must be the same as this symbolism. So here we go. Determinant of A minus lambda I. Well, the first thing that I'm going to do is I'm going to say that this is equal to the determinant of A minus I transpose. What I'm doing is I'm using this rule here that the determinant of A equals the determinant of A transpose. I'm using this fact right in my first step to say that, okay, even though this is written out as more complicated, it's still just a matrix. And I'm going to take the transpose of the matrix, and that should give me the same thing based on this rule. Okay, so let's see how that's going to get us to here. Now, if you look ahead, I'd really like to have the transpose with the A. Right now it's just A, but I'd like it to be A transpose. So this is where this rule comes in. You see this T, the transpose, you can distribute it out to the A and the B, and that's why we get that result. So let's apply that here. This is equal to the determinant of A transpose minus lambda I transpose. That's just using this rule, just putting the T into each of the separate matrices. So looking ahead again, what I'd really like is see, this is a problem. I've got lambda I, and lambda I transpose, and I really want lambda I. So you have to ask yourself, is lambda I equal to lambda I transpose? Well, let's take a look. Lambda I, what does that look like? That looks like a diagonal matrix with lambdas. And so it's a diagonal matrix. So and a symmetric matrix, moreover, so the transpose is equal to that. So this is equal to lambda I transpose, because it's a diagonal matrix. So I can write my next step, determinant of A transpose minus lambda I. And I've proven the exact thing that I hoped to prove. I started off with this was equal to that was equal to the next thing, and it was finally equal to the very thing that I wanted. And so I'm done with my proof. You can justify this last step as since, well, because of this fact. I'll erase this and then write that in. So here's the justification for this step. This is A plus B transpose equals A transpose plus B transpose. That's the justification for this step. And the justification for this last step is that lambda I is equal to lambda I transpose, as we saw. Okay, so the proof is complete.